in the previous lecture, we were discussing how exactly the data path control signals form the output of a microword, provided for each state we have an appropriate description. Okay. Specifically, we took for this particular state, and then we are working out the details of the code. Well, this is one way of implementing. All right. Good. I will come to this point a little later. Now, earlier we were talking about the state, that is specifically 4 states for instruction fetch, that is only one machine cycle, and we were working out the details. Now, what exactly is the purpose of working out the details? Essentially to design the processor, because the processor consists of data path and data path control, and these state signals actually describe the data path control, which helps set the data path. And then for one specific architecture, okay, we just took some typical architecture. We were seeing the data path in the previous lecture, and then I said that for one state, in case the code which we had arrived can be put in the memory, then one word in the memory will contain information about that control, data path control. And then I also showed with reference to the ASM chart, okay, showing the T1, T2, T3 and T4 states, how other fields in the particular word must also be added in addition to the control, namely next state and then some inputs which must be tested in each state. So, what do we have here? We have a microword which is specifically for one state, and you can see that once you store it in the memory, the address of a location in the memory is synonymous with the state. So, here address by address if you go, then the memory you can see has state by state information in each location, right. Now, as I said, this is one way of implementing. Okay. Now, to proceed further, we must know a few more things about these other fields, because in detail we worked out this output thing only for this T1 state. In general, if you just take any state, okay, any present state, call it A, okay, in general, nothing specific about any of these. In general, you have a state A. In that state A, which you call present state, some output may be generated. Then in that state, some input is also checked. Some input is checked, and depending on the input being 1 or 0, we said there are 2 possible next states, and we can call them as, say, state B and state C. Okay. Now, what it means is, for the present state A, if the input in that particular present state A, the input is 1, the next state is B. We say that B is the true next state for the present state A. On the other hand, if input is 0, the next state is C. We call C as the false next state of A. The true or false is really with reference to the input that is being checked in that state. Now, suppose this state happens to be T2. Remember, try to recall, in T2 we were actually checking the input condition, or rather we may say we are testing the condition of the signal ready, right. Try to recall what we have earlier, what we discussed earlier. In T2 we are trying to check ready, then depending on ready being 0 or 1, the next states are arrived at. In fact, I showed you 2 things. One is one next state may be T2, another next state may be T3, or one as TW, another as T3, whatever it is. Okay. So, now that particular information will have to be accommodated here. Okay. So, really speaking, the so-called next state field should indicate what if this test fails, meaning if the particular input that is being tested is 0, fails or it's false. Okay. Right. So, we must have in case the test fails, then we talk about a false next state. If the test passes, then we talk about the true next state. So, really speaking, the next state may be true next state and false next state. This will have to be accommodated, but there are ways in which this particular thing can be reduced to 1 also. We will talk about it a little later. So, now here you have given a state, that particular microword tells us what are the inputs which must be tested, and it tells us depending on the condition what are the 2 next states, true or false next state, and that word also gives us information about these signals which the controller must generate, that is output. The controller must output so that the data path may be set up. So, we have it for one state. Now, when you work out for all the states, now here we have just worked out some detail for one machine cycle. This will have to be done for all the instructions which the CPU support. Okay, the CPU supports, suppose it has say 250 and odd instructions. For each, the details must be worked out. But some of this will become common. For instance, this instruction fetch, as you can see, will become very common thing for any instruction, right? Now, this particular thing, if I can accommodate, yeah, in fact, I will be accommodating in 4 words like this, right? In 4 micro words, we will be accommodating because 1 for each state. Now, these 4, remember I was telling that it is a small step, and so we can even call each step as a micro instruction, right? Now, these 4 micro instructions together can form a micro routine. Okay, these 4 just these 4 micro instructions can form a micro routine. So, really the controller will have to will have to store these micro routines for all the data path it must set up and particular this thing. Then what about the sequencing? That sequencing information is available here. This is only for the data path setting. This is here you have the sequencing. It says, okay, is it state A? Fine. In state A, it says, if this is state A, this word will say test for some input. That information will be available here. Then it would also give these 2, true or next states. So, given a state, what is the data path to be set up, and given the state, what is the inputs to be tested, and what are the next states. Fine. Over. Now, this will have to be done for all the states. Then we have the entire control information in this memory. Since once you design a processor, these memory contents need to be only read, right? Because it is the behavior of it will be frozen once you have these codes, correct? Then you would find that this memory is nothing but a read-only memory, because subsequently only the contents of the memory will be read. So, read-only memory, and specifically since it is used for control purpose, this will be even called CROM or control read-only memory. Now, suppose you allow the user to change the contents of this memory, then he is going to change the behavior of this machine, because the sequence will get altered, is it not? The sequence will get altered. Then the behavior of the CPU itself will get altered. Okay. If that is possible, then we talk about a microprogrammable processor. Otherwise, this is only read only memory, which means it cannot be written, it can only be read. Then we freeze the behavior of the machine. Okay, good. And sets of words like this, as I said, form the micro routine, and sets of micro routines will form actually the routines needed for executing one instruction, and then you know sets of instruction form the program. So this is the way you go up from the lowest level to the highest level, that is the program level. Good. Now we must have some more information or understanding about the behavior of this. That is, in general I was calling as a state machine. So I will try to give some information, because this particular thing will have to be completed. Okay, all we have is some information about behavior for one state. That's all we have arrived at. Now I would try to give you a generalized state machine model, and then show you how this particular this scheme can be further developed. Now what is this generalized state machine model? Now you have some idea about the computer going into state, and state after state it moves, and then it executes some simple register transfer level activity. It carries out some activity. So essentially you can see that at any instant the machine, okay, or rather say I may be messing up like this. I may be saying machine, I may be saying system, I may be saying processor, right? I may be saying component. It's all just the same in this case. Okay. Now here specifically what we are talking about is a CPU as a component, which is an example of a digital system or a digital machine, right? Right. Now the processor will stay at any time in one state. Okay, in one state it will be staying, which means essentially I can use a memory element to show that at a given instant the processor is in one specific state. Now don't confuse this memory with the memory we are talking about in the overall computer system. It's different. Okay, this memory in fact stores the information, for instance, not very much different from this. Okay, the memory, if it is in state T1, okay, that's what I am talking about, then next instant it may go to T2. So correspondingly the content of that memory will be changing. In other words, to the input of this memory specifically there is a time input, which in fact gives, which we may call it as a state input. Generally the clock of a system will be for that. Now what exactly is the state memory? The memory holds a state, holds information about a state. By looking at the memory I can see, for instance, if this, for instance, that memory I am going to use to implement this ASM chart, then that memory, by looking at the memory I can say it is in state A or state B or state C. That's what you mean. Okay, good. The clock is the input to that. Then given a specific state, right, the output from that can be defined. Now I am going to complicate a little by introducing another output logic. Output logic. Then I will derive the actual output. So given a state, in a state it generates an output. That's what I have here. In a state it generates an output. What I have done is, given a state it generates some output, there is some logic behind the whole thing. Okay. Similarly, in each state I am going to receive some inputs now. Okay, in each state I am going to check for some inputs. So the input, I will also introduce logic for the input part of it. Now if I take this state information and feed to this logic and actually feed some inputs, these are the actual inputs coming from the external world. Okay. For instance, I can also take some of these inputs, say to this output logic. I will explain the significance of this. Now here, what you have inside this box is the state machine. Okay, there is a state machine. There is an input which defines the time, and then you have other, say, data inputs and data outputs for that matter. Okay, similar to what we had as data inputs and control inputs. That's what it is. Okay, you have some input, some output. There can be more than one, so I'll just do it like that. And here I have to complete this. Now see here. We'll just try to say this is in state A, and then some input must be tested. Depending on the input, the next state of this memory may be B or C, as just shown here. Depending on the input, it may be B or C, and then in that state it generates an output. So that's what you have here. Given the state A, in the state, the output logic helps generate some output, and in that state A, it checks for input and decides what must be the next state. So you can say that here you have this particular thing is performing a next state function. Okay, the next state function is performed for a given state. Now given the present state, now we can call this as present state. Okay, the present state. So given the present state, the next state is decided depending on the inputs, and given the present state, the outputs also are defined. Now as shown, the output is not only a function of the present state but also the input. Now this is one model. Now for instance, if you see here, I have not done any such thing. I am saying in present state A, some output is generated, call whatever, some output. I will just call it out1 or something. Now as per this ASM chart, in present state A, an output named out1 is generated. Actually, it is not depending on any input, no. So this is another model, in which case actually this link is not really there. That's what it means. Okay, in the generalized model we have this link. So sometimes it may not be there, in the sense the output is only a function of the present state if you don't have this. Agreed? So if the output is only a function of the present state, suppose I call this as G, okay, suppose I call this as say F in general, okay, then suppose I indicate the present state as X, okay, then all right, I will just make a small change because we generally use I will just call this as I for input. Yeah, I think just make change. You know why? O for output, easy to remember. Right, it's like this. O, and suppose the logic performed, this function logic function performed is, let us say, F, and the logic function performed, let us say, is G. Okay. Then in one model what we have is the output O is a function of not only the state x but also some of the inputs, not necessarily all the inputs, some of the inputs I. This is the generalized model. So output is a function of not only the state but also the input. Okay. This particular model is called a Mealy machine model. Okay, it's called a Mealy machine. Now on the other hand, if you do not have this, then the output is only a function of the state, right. Then this particular one is called a Moore machine. Okay. So you have different models like this. Well, the next state is a function of, as you can see here, the next state, what are the input? So I'll just put it as next, is a function that is g of x and I. Yeah, as shown here. The next state is a function that is g of x as well as I. Okay. So it's same thing as saying the next state is a function of I as well as the present state. Okay. Good. So in some we may have this link, in some we may not have. Specifically, as you can see in this case, as I already pointed out, this out one is depend only on the state, it is not depending on any input. There can be the other one not shown in this, merely output is not shown here. What we have there is only the Moore output. Good. Now this is very general. Now I am trying to tell you this mainly because have this in mind when we are going to develop further this particular one. Now what do we find here? This memory I said is the one which is going to store the state, and each one corresponds to a state. Okay. So suppose we have a system with say 52 states. Suppose you have worked out, and then you have worked out the design of a CPU, and you have arrived at, say, you have worked out the whole thing and there are 52 states. Now the 52 states, this is going to represent one after another, at any time only one. So you need how many bits? Suppose you use a binary code for this. With 5 bits you can have 2 to the power 5 32. So with 6 bits, so since 2 to the power 6 is 64, so basically you need a 6-bit code. A 6-bit code to represent a maximum of 64 is possible, but we are going to represent only 52. Fine. So it means basically what is a bit? Bit is a binary digit, and one binary digit is stored in one memory cell, right? And you all know that a flip flop can be used to store 1 bit, right? So having 6 flip flops in this memory, 6 flip flops, you can see that this machine goes through all the 52 states, right? Now with 52 states, now come to this specific thing. Suppose we have 52 states. Basically it means we need a memory of 52 minimum of 52 locations. That's what it means, because each location corresponds to a state, right? And at any instant the system stays only in one state. That's fine with us. At any instant you can only read from one location. So really what we are having here is a 6-bit code that is I am talking about 52 states, 6-bit code. A 6-bit code comes here, right, and here you can have 1 of 2 to the power 6 output. So really this particular decoder is the decoder output is always 1. So here it is from 2 to the power 6 to 1, that is what the particular decoding will be taking place, right. So really we say the output will be 1 of 2 to the power 6, that is what you have, okay, for this specific example. If you take n-bit code, the address decoder will be 1 of 2 to the power n in general. Good. Now what it means here is on this side, we must have the memory element so that there are these 6 flip-flops. Let us say if we are implementing this flip-flop, then what we need is 6 flip-flops here, okay. So 1, 2, 3, 4, 1, 2, 3, 4, 5 and 6, okay. So 6 flip-flops if you have, why don't we just call them FF0, FF5, let us say. And what do we have here? Next state. I said of true next state and a false next state. One of these will be selected. So really this next state, that also will be a 6-bit code, right. So 6 bits for true and 6 bits for false. Actually the whole thing will be 12. At any time only one of these will be used. So we would have a selector here, we will have a selector here to either pass on the true next state or to pass on the false next state, which is again 6-bit code. And there will be a control signal. What is a control signal? Because this particular, essentially it's a multiplexer, okay. Essentially it's a multiplexer which you have seen earlier. So which passes on either this leg out input or this leg input onto the output, okay. What we need is essentially a 6-bit next state code. For the present state, the whole information is available, and it says depending on the test. So we have to take a look at the test. Depending on the test being false or true, one of these will be passed on, right. Right. Why don't we complete that? One of these will be passed on, and that particular thing will go here. That is 6-bit. It's a 6-bit code. Okay. And we going on to that. Agreed? Now, which of these to pass on? That depends on. We must have a selector logic here. Okay. Or why don't we call it as a simple test logic? A test logic, the output of which is really used to select either false or true. Next stage. So test logic. So this there may be many, we don't know how many bit wide that particular thing is. Okay. Suppose you allocate, see what is this? It's a memory word, no? Suppose you allocate 4 test bits. Possibly 4 signals are being tested, that's what it means. Okay. There are many other ways of looking at it. Okay. And the actual signals from the real world will be given here. In other words, the actual inputs which must be tested, which come from the real world, okay, they will be given here. For instance, one of these in our case, okay, just one of these in our case may be this ready signal, which is needed, right? You recall what we had in T2 state T2, you are checking whether the ready is 0 or 1, right? So that information will be coming to this, and it's shall we work out that? Why not read this way? Suppose this is T2. Just alter this. Yeah. Suppose this is T2 state. Well, there are two outputs here. These are the two outputs. And then ready is the input that is being checked. If it is 0, remember when one we were saying it goes to the next state, wait. If it is 1, it goes to the next state, T3, which here corresponds to this. So ready in fact is an input to be checked during T2. That information must be available in this. Suppose this were for T2, this particular one, this word, okay? This word is for T2. The test field in this must indicate that in T2 ready is a signal which must be tested. So it's only information that comes. This whole word comes down here. So this test field will indicate ready is the input which must be tested given the state, and the actual input signal will be going to this logic. So basically it's only information. It says check for the state of ready, and then depending on ready being 0 or 1, ready being 0 or 1, if ready are 0, pass on the next address as what? That is the address corresponding to TW. Okay, what will be a 16-bit code. Okay, so this F will correspond to TW, the code for TW. Okay, otherwise if it's true, it will say this particular one T will correspond to the 6-bit code corresponding to T3. Right? Now you have the whole picture, how the sequencing of the states is going on. So start from any state. In that state, you have information of what are the inputs to be tested, what are the possible next state the machine can assume, and what are the set of output signals which must be generated. In our case, these output signals, they are all for setting the data path, right? So here you have a ROM based implementation of the controller. Okay, now here you have the microprogrammed controller, mainly because the whole control aspect is in the form of microprogram. Agreed? Now this is one implementation, as I was telling you earlier. This in fact is called a firmware implementation. Why do we call it firmware? Because as long as you have the code, all the code for all the states here and frozen, you don't change anything, the behavior of the machine is there all the time. You're not changing anything. It's firm enough. But then suppose I remove this particular memory chip and put another memory chip with different codes. The behavior of the whole machine is changed, no? So it offers me a flexibility, right? That's why it's not hard, same time it's not soft, so we say it's firm, right? For you to gain an understanding of what would be a hard-wired controller or hardware-oriented controller, I will take an example, but unfortunately I cannot take CPU design in the lecture, right? Because it consists of many states. I'll just take an example of just 4 states and then work out the same thing for you, and then I will show you the hardware as well as the firmware, so that you can have an idea about what would be a hardware controller. Okay, we'll come to that later. Now this particular one is a ROM based implementation, which is essentially a firmware solution of a microprogrammed controller. Fine. Now let's quickly work out. The read-only memory will have the information about all the states. When I say all the states, I mean all the states for all the machine cycle, for all the instructions of the processor, right? Controller. Given any state, the details in that will be such that it will tell what is the output to be generated in that state. For instance, in T2, these are the outputs to be generated. Okay, that is, read control signal must be placed on the control bus, and program counter contents must be incremented. These in fact are done in parallel because they go to different parts of the processor, whereas these, they all in sequence. So these two both are going to different parts of the processor, and so you can have these things implemented in parallel, right? That's what it is. Okay, so these outputs are generated in T2, and it says in state T2 check for ready input. This information will be available here, right? And depending on the ready input being 0 or 1, the two next states, true next state and false next states, the codes of these will be available here. And depending on this, whether the test has passed or not, depending on 0 or 1, okay, there is a control. Depending on 0 or 1, which depends on this particular one, either this or this will be passed on to this. Now here also to this what is called a state generator. This in fact is called a state generator, right? With this you are generating all the states. In fact, sometimes it's even called a major state generator. To this also the clock will be given. The same thing, where else are you using? Oh, here's the place where you are using. Here, the generalized one. You see the state input you are saying, no? That's the clock. So the clock is the one which goes to this memory. So now are you able to see clearly? This memory is a state generator with the clock. That's what you have here. And there is some input logic to which inputs from the real world go. You have it here, right? And the next state function has been implemented. That part of it is also here. And the output is generated, or set of outputs will be generated. That part of it in this case is available here. The details of which we saw in the previous lecture. So this is how you have the control of a data path. Now you can see that data path is set up having the appropriate sequence of the control signals. Really speaking, data path and data path control are not really different, right? Maybe it's like our body and soul, is it? Whatever it is, somewhat like that. Okay, because the data path is always there. There is this, all the data paths combination, they are all physically available. Only when the control signals come, the paths get activated. So like our body and breath force or soul, whatever you want to call it, that's what it is. Good. Now this is one, as I said, one implementation only. Okay. And as I already explained, this implementation has the flexibility mainly because it is not completely wired. What we mean is, the ASM really gives you the behavior of the whole machine. ASM chart you see the behavior of the whole machine, and that in terms of codes this read-only memory is going to have, correct? Now instead of these codes, if you pull out and put another memory with different codes, the whole behavior is going to be altered. So the read-only memory through its codes actually capture the behavior of the whole machine. Good. And since one can change, one doesn't change just like that. When one can change, we say it is firmware. Now in the case of hardware, later on I will show you, it's going to be very difficult because the whole thing will be wired. You can't change. For instance, you can't change things here. These are all hardwires only, hardwired part of the circuit. If you want to change anything, you have to remove all the things and then desolder and whatnot. Okay, these are all. So in a firmware implementation, the essential thing will be in a read-only memory flexible form, but then associated with that there will always be hardware. But the behavior of the machine will be available in such a way that you can change if you want. That's what it is. In the case of hardware, there will be problem. Good. Now I hope you got enough. You are able to map this generalized state machine model with this, and then understand what's going on here with this, right? That's what the whole thing is about. We were just looking at the microprogrammed controller and how to design that. And then I said it's essentially a firmware realization. And then I also mentioned that there is a hardware realization of the same circuit. Now, for a complex system such as CPU design, a CPU, and to design that particular thing, it's going to be very difficult discussing through lectures like this. So I will take up an example of a digital component, a simple one, which have a few states and a few inputs to be tested and a few outputs, and then work out the system design of it both from hardware point of view as well as from the firmware point of view, and then try to show you the parallel between this and what we have seen for the CPU. So for this, taking up the design of a flip-flop which stores either 0 or 1, specifically to accommodate a few inputs will make it a little complicated. In the sense, we'll take up the design of a master slave flip-flop. I'll explain what this means, and one specific type of flip-flop called JK flip-flop. Okay, this is the one we will consider. Good. Now J and K are the actual inputs. So let us just take a look at the set of inputs and the outputs that the flip-flop must generate. Since I said essentially a flip-flop contains either 0 or 1, right? The output must be just one of these. We'll just name one as H0, okay, and the other output as H1. That's all the output is. There is something more which must be said for the master slave. We'll talk about it a little later. Now as for the inputs, this particular flip-flop has two inputs called J input and K input. We'll just name these inputs as, say, Yj, okay, J input, and Yk, the K input, and then any system will be having a clock, okay, especially if it's a synchronous system, there will be a clock. So you just call that as Yc. Now as you can see that we are putting just the prefix Y for the inputs and the prefix H for the outputs. Just while naming it, just a naming convention, nothing more. Okay. Then you may be knowing about this JK flip flop. I'll just briefly tell what it is. Okay. Now J and K are the inputs I said. Okay. And then the output will depend on the state of these, as well as in the case of flip flop you have to also take into account what was the previous state, and depending on the input what is the next state. Okay. Now if you have these as the inputs, and if the present state of a flip flop is something, what happens to the next state? This is what we have got to take a look at. Now, what we are currently going through is defining this system, namely master slave JK flip flop. Just we are defining that. Now the present state, if it were say 0, and if J and K both the inputs are 0, the next state is also 0. Roughly you can take it that J is something like setting the output and K as resetting the output. But generally we use the word set to set the flip flop output to 1. We use the term reset to reset the flip flop output to 0. Okay, set, reset. Good. Here we find that it says do nothing. On the other hand, if you have J, or if the present state is 1, then with J and K both 0, the next state continues to be 1. In other words, what we have is there is no transition between this. This is what it means. Okay. Now, if the present state is 0, and if you have K input is 1, I said K is something like reset. Reset means 0. So the effect of that will be to see that the output is still 0. Now on the other hand, with J0 and K1, present state is 1. Now this says effect of K will be to reset, that means 1 must be reset to 0. That's what it is. So like this we have to go on, which will describe the whole behavior of this JK flip flop. Now what is the next? Next would be this one and then you take J1 K0. Effect, I said J means set, no? So that means next instant, next state of this must be to set, that is to become 1, to make the output 1. On the other hand, if it were 1 already, well, if J is 1, K is 0, the output will continue to be 1. Okay? Then we have two more conditions to be checked. It's namely, if the present state is 0 and J and K both are 1. Now our definition of set reset fails here because one says set, the other one says reset. Okay, for this particular condition, now when for two input conditions it will occur when the present state is 0 and when the present state is 1. So that is in these two conditions. Elsewhere it is either J is or K, okay, only one of them is 1. Here is the only two input conditions for which both J and K are 1. Now for this we don't talk about set or reset, we say if both happen to be 1 it toggles, meaning whatever the state it is, it just goes into the other state. That means if the present state is 0, the next state will be 1. If the present state is 1, the next state will be 0. Now this in fact is the behavior of the JK flip flop. I have not yet explained what the master slave is. which we will take up in the subsequent lecture, and also work out the ASM chart for this behavior, carry out the design both hardwired as well as firmware. Okay, these two approaches, we will see it in subsequent lectures.